One more example of multiple linear regression, example that comes from the world of sports analytics. We're gonna refer to Dave Pelt here. He is the author of two best-selling books on this topic. Specifically, he wrote about analysis of golf data. The two books are Short Game Bible and Putting Bible. Before he became a sports analyst, he was literally a rocket scientist, and he was basically trained in how to do data science, applied to some engineering problems, and started applying the same set of skills to analyze the performance of golfers. And he essentially made a career, and he became a consultant. He would consult top golf players. And one of the ways he would do it is by purely analyzing data from those golfers. And baseball was one of the first sports where sports analytics became widely used tools by coaches and team managers. Golf is another example. Nowadays, pretty much any sport would heavily rely on analytics, and behind most of the analysis is essentially a regression model. And the regression model usually helps us to understand the relationship between the performance of player and game outcome. So what we want to usually model in the sports analytics, so we're going to have our model, and the outcomes are going to be the outputs, and characteristics of player or a team, if it's a team sport, or if it's a team sport, it's going to be individual players plus the team. Then we're going to model the relationship between the characteristics and the outcomes. And outcomes can be the number or percentages of wins. In this case, for the golf example, we're going to analyze the prize money, how much money was made by each of the players and how it relates to the actual skills of the players. Okay, and let's look at the data. So we have 2000 data from the PGA Tour. 195 players participated in the tour, and for each of the players, we have a record. So player is our observation. Okay, so we have 100 our n, the number of observations 195. And so for each of the players, though, there's the variables we have in the data set. So there's the columns, number of the events, so how many events this player participated in, prize money, so that's going to be our y variable. Green in regulation, so it's measured as percentage of time that the first tee shot on par 3 hole ends up on the green. Or the second shot on the par 4 hole ends up on the green. So essentially you have, if you can make it into this green circle in one less attempt that is allowed. So if you have 3 attempts and you do it in 2 attempts, that's basically green in regulation. And average puts is the average number of puts per round. And now we want to analyze this relationship between all of those variables and this money variable. So in this case, the y variable is going to be money, the prize money, and then we're going to regress it to the number of events. Actually, all the variables that you see on the screen will be used in the regression model. So let's just go ahead and feed the model. We're going to use the lm function. We're going to put all the variables into the model, and let's first look at the economic significance or the values of those estimated coefficients. So the intercept is some non-zero number here. Now the intercept here does not have a nice interpretation as we had, for example, in the housing data set. What intercept tells us, if you participate in 0 events and your average drive distance is 0 and the green regulations is 0 and average putts is 0, then you're going to make $1.4 million, which of course doesn't make sense. If I show up having no skills, not participating in any events, I'm not going to make $1.4 million. So we have to be very suspicious about this prediction from the model. So the prediction from the model for one number of events and all other variables is 0 actually doesn't make any sense. Let's look at the number of events. It looks like it's so number of events is negatively related to the money. Why is that? The more events you participate in, the less money you make. From the first glance, it's counterintuitive, but if you think a little bit deeper about this, what happens is usually top players will participate in a very small number of top events. So they focus all of their time and attention and efforts on those top events, and they will focus on winning those. Players below this top group of players, they will basically try to build their rankings, and to build their rankings they have to participate in the small events because they have low chance of winning top events, so they try to build some scores by participating in small events for which they have a smaller number of prize money. So it's essentially the relationship between top players and non-top players. That's why top players would make more, because they will win those top events. Drive distance positively related. Yes, the longer your ball flies, the better you are a player and more chances of winning a tournament. And green and regulation has a huge impact, of course. The faster, the smaller number of attempts you can use to bring the ball into the green circle, the better. And of course, average puts has a negative effect, so the more attempts you try at the very last part of the game, the less likely you are to win a tournament. And let's look at the statistical significance. Actually, for all of those variables, the p-value is less than 0.05. So at this level, all of them are significant. In actual R tells you the significance level by showing this 3 stars here. So 2 stars means it's significant at 0.01 level, and 3 stars means it's significant at 0.001 level. But in our case, we just care about this 0.05 threshold, so all of them are significant. So put a check mark for all of them. And let's look at the standardized residuals here. Remember, the residuals should resemble the normally looking random variable. So you should be able to imagine to put a bell curve on top of the histogram of the residuals. Which is almost the case here. There is one outlier we have here on the right hand side, and it happens to be Tiger Woods. So Tiger Woods is essentially, so let's think about this. So residual for Tiger Woods is large. And what is the residual? Residual is y hat. So the amount of money model predicted that Tiger Woods is going to make minus y, which is the actual amount of money Tiger Woods made. And why this difference is so large? So essentially what model tells us that Tiger Woods made disproportionately large amount of money, disproportional in reference to the skills of Tiger Woods. And again, this is the same story, top player versus non-top player. Tiger Woods is the top player. He focuses on the top events, but not only he focuses on them, he actually has ability to win them. So although maybe his technical skills are not that far away from his competitors, but maybe his mental skills are much stronger, which we do not observe in this model, so we don't measure how strong he is mentally. But there is something about Tiger Woods that is not represented in our observed variable that makes him winning those top tournaments. And again, most likely it's just his ability to cope with stress and perform well in the final rounds of those top events. That's what essentially makes a very technically good player to be an exceptional player, and the top player, its ability to cope with stress. Now let's see if we transform money in the logarithmic scale and we keep the rest of the variables on their original scales. Now number of events actually become insignificant, and the rest of the variables are still significant. Our R squared is slightly high compared to the previous model. So again, in this case, we actually can use R squared maybe as a proxy for how well model does. So it looks like it's this model is slightly better, slightly better compared to the previous model when money was on the original scale. And let's look at the residuals. Actually, residuals also look better. So the residual analysis tells us that putting money in the log scale was a good idea. It made model look more like a linear model, so the assumption of normality are satisfied closer here compared to the original model. So you see, even though we have an outlier, but the outlier is not as strong. So essentially here, Tiger Woods is 3 standard deviations away from the average player in terms of how much money he made on the logarithmic scale. So that's how we interpret this outlier here. Okay, and so we exclude the number of events. Looks like when you put money in the log scale, it doesn't matter anymore. The p-value is above the threshold. And we're gonna build our final model, which we'll use for the analysis. So the money in the logarithmic scale, number of events was eliminated from the model, and those are the coefficients. And the sign of the coefficient stays the same, right? The average number of puts is negatively related to your chances of winning prize money. Again, this is trivial and nothing interesting about this. Green regulation positively related, and drive distances is also positively related. All right, so and again, all of them are significant. Let's look at the absolute values of those, and let's make some conclusions about the relationship about prize money and the technical skills of the player. So for Greenland regulation, we have the coefficient 0.16, so I rounded here to 0.17. So our beta hat associated with the 0.17, and you remember that in the final model we had money in the log scale. So to put everything back to the linear scale, we have to take exponenta on both of the sides. And so we have, once we hit exponenta, then we take this beta becomes exponenta raised to the beta. So e to the power 0.17 becomes 1.18. So extra 18% means that if green in regulations go up by 1 on the additive scale, money go up by 18%. So you can increase your earnings by 18% if you just can improve green regulation by 1, which is very hard to do. Okay, and the drive distance is 0.014. So again, we take and raise it to the exponenta, and we change the units here. Instead of having 1 yard as a unit, we do 10 yards. So we'll look at the 10-yard improvement. So 10 times 0.14, and we take exponenta of that, 1.15. Again, so if your drive distance go up by 10 yards, your money will go up by 15%. Okay, so again, we had y variable in the log scale, and the rest of the x variables were in the original scale. So when the x changes on the linear scale, y changes on the multiplicative scale, on the percent scale. Okay, and of course everyone got better since 2000. So if you try to analyze it and give some recommendation to the modern day players, then you have to use the new data set, because those coefficients might not be valid anymore. But based on the model that we have, so here are a few findings. Tiger Woods was 9 standard deviations better than the average player, at least on the linear scale. Once we took the logarithm of the money, it helps us with residual. It started looking more like a normal histogram. An exponential model seems to fit well. The residual diagnostic looked good, and the number of events became insignificant variable when we put money on the log scale, and we excluded from the model. So let's look at the residuals and let's try to look at the overperformance. So overperformance means that the person made much more money than it was predicted by the model. And again, model predicts the amount of money based on the technical skills of the player. So Tiger Woods, the model predicted Tiger Woods supposed to make $3 million. So actually, if you look at the second best, Phil Mickelson, model predicted 2.3 million. So Tiger Woods shouldn't be that far away from the Phil Mickelson based on the technical characteristics, but in terms of the money, Tiger Woods actually made more than twice as much money compared to the Phil. And again, the error for the Tiger Woods is 5.6 million, so he is far away from the average player based on the fact that he just can cope with stress and can win those high-profile events. And in the same way, we have underperformance, meaning those are the players, actually, the model predicted 1.9, almost 2 million for Kenny Perry. Actually, it's very similar to Phil Mickelson, who is the second person in the overperformance list, but he actually made less than $1 million, so he's 1 million away from the value predicted by the model. Again, that's basically technically very good player, but player who doesn't cope with stress very well, and does not get to the finals and to the winning podiums in those high-profile events. And this is data for 2018 now, so we can do the same type of analysis, look at the overperformance and the underperformance. And again, so based on the predictions from the model, we can start giving some recommendations to the players. The same for the 2020 data, so if you a golf fan, you might find this interesting. So Bryson DeChambeau, of course, was the biggest overperformer. He essentially was equivalent of Tiger Woods in 2020. All right. And to finalize the findings from the original model, Tiger Woods is an exceptional player. His earnings are way above his technical levels. He's 8 standard deviations better than the average player. And if an average player, if a player can increase the drive distance by 10 yards, the player will increase money by 15%, and the green regulation goes up by 1, your money go up by 18%. Okay, and then we can detect over and under performance. And so we use the model to understand the relationship between technical characteristics and the money, and we also can use this model to do some recommendations for the players, especially for those who are under performance. We can say, hey, you actually have good technical skills, you actually can achieve better more in the sport, and we can find those little tweaks that would help you to basically get to the level of prize money that corresponds to the technical skills.